What's up everyone, and welcome. In this episode, we're going to talk about a new Linux kernel bug that can allow remote code execution. The chances are, you have no idea about this, or even if it affects you. And that's a problem. Let's review the story together and get an understanding of whether or not it actually affects your systems, and then we'll see what we need to do to make sure that we're never guessing whether or not an important or dangerous bug like this actually affects us.
Oh, drat these computers. They're so naughty and so complex. I could pinch them.
A critical heap overflow security vulnerability in the Transparent Interprocess Communication (TIPC) module of the Linux kernel could allow local exploitation and remote code execution, leading to full system compromise. TIPC is a peer-to-peer protocol used by nodes within a Linux cluster to communicate with each other in an optimized way. It enables various types of messages that are used for different purposes. According to SentinelOne's SentinelLabs, the bug in question, CV 2021-43267, specifically resides in a message type that allows nodes to send cryptographic keys to each other. When received, the keys can be used to decrypt further communications from the sending node. When loaded by a user, TIPC can be used as a socket and can be configured on an interface as an unprivileged user, explained SentinelLabs researcher Max van Amerongen in a Thursday posting. All message construction and parsing is performed in the kernel. This makes it an ideal target for attackers. As for the heap overflow, when it comes to that message construction, every TIPC message has a common header format. According to the researcher, that common header contains a header size allocation, which is the actual header size shifting to the right by 2 bits, and a message size allocation that is equal to the length of the entire TIPC message. These two sizes are validated by the TIPC_message_validate function. The message size is correctly validated as greater than the header size. The payload size is validated against the maximum user message size, and the message size is validated against the actual received packet length, and Amerongen said. So far, so good. However, a new message type was introduced in September 2020 that lacks such size validations, opening the door to a heap overflow exploit. So, prior to September 2020, all of the message types had this size validation. With this new message type in September 2020, this new type did not include that size validation, which allows the heap overflow. The additional message type, which is called message_crypto, allows peers to send cryptographic keys to each other, as mentioned. The messages contain the name of the key algorithm and the key itself, according to the analysis. The size allocation for this is the message size itself, minus the header size. However, there are no size validation checks for either the key length or the size of the key algorithm name itself against the message size, the researcher explained. This means that an attacker can create a packet with a small body size to allocate heap memory, then use an arbitrary size in the key length, or key len, attribute to write outside the bounds of this location. Also, the message validation function only checks that the message size in the header is within the bounds of the actual packet. That means that an attacker could create a 20-byte packet and set the message size to 10 bytes without failing the check. The bug affects Linux kernel versions between 5.10 and 5.15. It should be noted that while the TIPC module comes with all major Linux distributions, it's not on by default and does need to be enabled in order for an implementation to be vulnerable to attack. To protect themselves, affected Linux users should apply the just-released patch, which adds appropriate size verification checks to the process.
Couple of inches too short. Well, we can fix that. You made it, boy!
The stakes are significant, researcher warned. While TIPC itself isn't loaded automatically by the system, but by end users, the ability to configure it from an unprivileged local perspective and the possibility of remote exploitation makes this a dangerous vulnerability for those that use it in their networks, warned van Amerongen. What is more concerning is that an attacker that exploits this vulnerability could execute arbitrary code within the kernel, leading to a complete compromise of the system. Linux kernel bugs aren't that common, but they do crop up occasionally. For instance, in April, an information disclosure vulnerability CV 2022-8588 was reported that could be exploited to expose information in the kernel stack memory of vulnerable ARM device. So, what can we learn? Besides beating a dead horse by saying, keep your systems patched and up to date, I think here we need to look at our documentation and see if we have all our systems and software documented. This is important so that we can check regularly to see if any of our infrastructure has a known bug. Now, I'm not saying that you need to go out there and start debugging or testing the actual Linux kernel for bugs yourself. I mean, knowing that you're running system, say, Ubuntu 18.04 long-term service, LTS, or you're running a Linux kernel 5.10 to 5.15, you need to be registered with the respective organization to be notified about updates and patches and vulnerabilities for those systems. Or you could just scan CVEs yourself, as long as you know the system that you're trying to scan. Now, my point here is this story may or may not affect you. You won't know unless you know A, if you're running Linux systems, B, if any of the Linux systems are using kernel 5.0 to 5.15, and C, did you or anyone responsible for these systems manually enable TIPC module? A and B may have been very easy to answer, but is C very easy to answer? You don't know. So this is why you need good infrastructure documentation. With that, I say thanks for watching, don't forget to share, and subscribe if you haven't already, and smash the bell if you haven't already, and I'll see you on the next episode. Take care.